Assalamualaikum. We are from Group N, and we are going to present about design of a harmless bladeless fan using electromagnetic air propulsion.
So, for the background and introduction of our projects, I want to talk about how we cool our rooms and why we need a better way to do it. Let's start with the conventional fans. We all use them and they are cheap and work well, but they have some problems. The spinning blades can be dangerous for kids and pets. They can be very noisy and the motors wear out and break over time. To fix this, we made the bladeless fans. They look modern and are much safer because you can't see any blade on it. But here's the secret. They aren't actually bladeless. They still have hidden fans and motors inside the bottom part to push up the air. So this is where our bladeless fans come in. They are using different technology called EHD and ionic wind. This technology creates airflow with zero moving parts. As you can see in the picture, we use electricity to charge the air particles. These charged particles shoot forward toward a collector. On their way, they bump into regular air particles and push them forwards, creating a smooth stream of wind. Because of this fan has no moving part, it gives us 4 great benefits. It's very quiet because there's no noisy motor. It lasts longer because there are no parts that wear out or break. And then it's small and lightweight. And it's completely safe since there are no spinning blade at all. Now, let's look at why we need to change how fans work. We have found 4 main problems with the standard fans today. First is safety. Standard fans use fast spinning blades. If someone touch them by accident, they can get hurt. This is a big worry for families with young children and pets. Second is noise. The spinning blade and the motor make a lot of buzzing noise. This can be very annoying when you are trying to sleep in your bedroom, focus in an office, study in a library, or rest in a hospital. Third is maintenance. Because these fans have moving parts like motor and bearings. They rub together and wear out over time. This means they break easily and need to be fixed or replaced. Lastly is airflow efficiency. Standard fans relies entirely on how fast the blade spins. This makes it hard to control the airflow smoothly, and it wastes a lot of energy.
Next, I will explain our proposed solution. Our project proposes a harmless bladeless fan that uses electro-hydrodynamic or EHD propulsion instead of conventional rotating blades. We chose this approach because conventional fans have several limitations, such as safety brakes, noise generation, and mechanical wear over time. Therefore, we wanted to design a safer and quieter alternative. The first part of our system is the EHD propulsion mechanism. Inside the fan base, sharp emitter needles are connected to a high voltage power supply. We use sharp needles because they can create a stronger electric field at their tips. While high voltage is applied, the surrounding air molecules become ionized, which means they gain an electrical charge. Above the emitter needles, there is a grounded collector mesh. The positive ions are directed toward this mesh. As they move upward, they collide with surrounding neutral air molecules and transfer momentum to them. This process creates airflow without using any rotating mechanical components. However, one limitation of ionic wind is that it produces a relatively weak airflow compared to a normal fan. To solve this problem, we added an aerodynamic housing at the upper section of the fan. The air enters a hollow airfoil ring and exits through a narrow 0.8 mm slit. Due to the Conda effect, the airflow naturally follows the curved surface of the ring. This creates a low pressure region that pulls in surrounding air and combines it with the original airflow. As a result, the total airflow can be amplified by around 15 to 20 times while still maintaining a smooth and continuous airflow. Next, I will explain the drawings that represent our proposed design. The first diagram shows the overall structure of the bladeless fan. The lower section contains the air intake and high voltage power supply, while the upper circular ring distributes the airflow. The second diagram shows the EHD acceleration channel located inside the fluid base. The emitter needles ionize the air, while the collector mesh attracts ions and helps generate airflow through the electromagnetic forces. The last diagram shows how airflow amplification occurs inside the upper airfoil ring. The airflow exits through a narrow slit and follows a curved surface due to the conduct effect. This creates a low pressure region that draws in more surrounding air. Overall, this design allows us to produce a safer, quieter, and low-maintenance cooling system without exposing users to rotating plates. Thank you.
Okay, next for the methodology, this study adopts a conceptual and literature-based approach to investigate the design of harmless bladeless fan using electromagnetic propulsion. So the first stage is literature review, where we studied previous research on conventional fan, electrohydrodynamic or EHD technology, and bladeless airflow system. So this helps us understand the existing technologies, their advantages and their limitations. So next is technology analysis. In this stage, we analyze existing bladeless fan technologies, particularly the airflow generation mechanism and aerodynamic design. The third stage is conceptual design formulation. So, where the knowledge gathered from the literature was integrated to develop the conceptual design of our purpose bladeless fan. And finally, the last one, the purpose concept was evaluated theoretically by comparing it with a conventional fan system in terms of safety, noise generation, mechanical complexity, and maintenance requirements. This evaluation was based on findings from previous studies to determine the feasibility of the proposed concept.
Okay, good morning, afternoon. In this session, I'll explain the three fundamental principles that make our bladeless fan work. So there's three sections. So first, we use electrohydrodynamic propulsion to create ion wind without moving parts. And the second, we transfer momentum from charged ions to neutral air molecules. And third, we amplify this weak airflow using the Coanda effect to achieve practical cooling performance. So here we have the slide of electrohydrodynamic propulsion. So our system uses an asymmetric electrode configuration with a sharp needle emitter at 15 kilovolts and a grounded collector mesh. So the key principle here is that the electric field enhancement. So according to the relationship E equals negative del V, the sharp curvature of the needle tips creates an extremely high voltage gradient. So this voltage sees the ionization cathode of air, so producing corona discharge. So we also apply Poisson's equation to model the space charge region, where rho V represents the volume charge density created by ionized molecules. So this allows us to predict how the electric field distributes between our electrodes. Once the air molecules are ionized, they will experience an electrostatic force defined by the Coulomb's law, which is F equals Q times E. So the positive ions are accelerated towards the grounded collector by this force. So the ion velocity depends on the electric field strength and ion mobility, where mu is approximately 2 times 10 to the minus 4 meters squared per volt second in air. So this acceleration is what initiates the airflow generation process. So as the ions accelerate through the inter-electron gap, they collide with neutral air molecules, primarily with nitrogen and oxygen. Through this collision, acceleration, momentum is transferred from the ions to the natural molecules, creating what we call ionic ring or electric field. So the body force density driving this flow is given by rho c times E, where rho c is the charge density. So given that, the major advantages are clear. So there will be no rotating blades, silent operation, and zero mechanical wear since this is a solid state system. So now let's verify our design with theoretical calculations. With a 10mm gap and 15V applied voltage, the average electric field is given as 1.5 megavolts per meter. So the average field is below Earth's dielectric proton strength of 3 megavolts per meter, preventing a complete electrical arc. However, the localized field at the sharp needle tip far exceeds this threshold, successfully initiating stable coronal discharge. This gives us the best of both worlds, ionization without short-circuiting. Using the macroscopic EHD thrust equation, F equals I times D divided by mu, we calculate that the theoretical thrust with a typical coronal current of 100 microamperes, our charge is only 0.005 newtons. This calculation is crucial mathematically, prove why we absolutely need the Quenda airflow housing. So without the amplification, this system would be useless. But with 15 to 20 times amplification, we achieve an effective thrust of 0.075 to 0.1 newtons, which is sufficient for personal cooling applications. For future prototyping, we propose a multi-physics computational modeling using COMSOL. We'll couple two physics interfaces. First, the electrostatic interface to evaluate high voltage field distribution and ensure our field intensity stays within safe operational limits. Second, the fluid dynamics interface will model ionic wind as a body force defined by rho c times E. The simulation will provide velocity vector fields showing air entrainment and validate our projected 15 to 20 times amplification ratio. This computational approach allows us to optimize the design before physical fabrication. So lastly, with our conceptual design and academic research, here is how our EHD bladeless fan compares to a normal conventional fan. While conventional fans operate at 14 to 16 decibels with exposed rotating blades, our system operates below 20 decibels with zero exposed moving parts, making it 100% safe. But maintenance is minimal since we have solid-state electrodes with no friction. The trade-off is, however, moderate energy efficiency due to high voltage conversion losses. However, the fundamental account is clear. We've designed an intrinsically safe, acoustically neutral cooling device with minimal maintenance requirement.
This Gantt chart illustrates the overall schedule for our purpose study, which was carried out over a period of approximately and a half month, which is from 13 April until 1st July. So the project began with topic selection, problem identification, and objective formulation, which we took 15 days. So the next stage was task division, which required 2 days. Each group members were assigned specific section of the report according to their responsibilities to ensure an organized workflow and avoid overlapping work. So after the task allocation, we conducted group discussion for almost 15 days to exchange ideas and ensure that every section of the report was technically consistent and aligned with the project objectives. After that, we followed by the individual work phase, which lasted 13 days. So during this period, each member independently completed their assigned tasks, including researching relevant literature, preparing technical drawings, writing report section, and collecting supporting references. So once all individual sections had been completed, so we took 9 days for report writing and compilation. Okay. After the report was completed, 3 days were dedicated to preparing the presentation slides. So after that, followed by 5 days for video recording and editing. Um, Finally, the last 8 days were reserved for final review and submission. So during which the group carefully checked the report, presentation slides, figures, references, and video before submitting the completed project.
So, in conclusion, this project successfully designed a safe and low-noise bladeless fan by combining electro-hydrodynamic HD propulsion with the Conda effect. Instead of using rotating blades, the fan generates airflow through a high-voltage current discharge, while the airfoil-shaped loop helps increase the airflow by drawing in the surrounding air. Since there are no moving mechanical parts, the design is safer to use, produces less noise, and requires less maintenance than a conventional fan. Overall, this project shows that EHD technology has good potential as an alternative approach for developing safer, more efficient, and environmentally friendly air circulation systems in the future.